All right, Asa, today I think I'm going to try and talk about quantum tunneling. It is very weird. It makes very little sense. It's one of the things that about tiny scale physics, which is that you can't comprehend it because it's not in our everyday lives, so you don't have an intuitive sense.
So this is where I tell you I lied a bit. In the real world, instead of having those histograms of probability, we end up with curve of probability, which its area equals to 1. And technically, the tails never reach 0, but they get so close. They're practically 0 in both directions. And this is our particle. Makes sense to think of a classical example first and then talk about why the quantum world differs. I'm going to use hills in terms of energy levels, but know that energy doesn't have to be hills per se. That's just the easiest for us. You've got your valley, right? So this is lower than this one, just do. And think of it as this is the energy level of your particle, and then if it goes lower, it gains kinetic energy, right? So like you roll a ball down a hill. It starts up here, it's got potential energy from gravity. As it rolls down here, it will have relatively 0 potential energy from gravity, but it will have a bunch of kinetic energy. And so it'll actually roll up here to the same level, to the point where it stops moving, because all of that kinetic energy has been put back into the potential energy. But because this hill is higher than the energy put in the particle by starting it up here, it will never cross this hill and keep going. There's no way around that in classical physics. But because God really did wake up one day and choose violence, it's different at the quantum level. So remember that these are energy levels, not necessarily hills, so the particle isn't moving along them per se. If the energy level changes at a state that's below the energy level of our quantum particle, which is this probability wave, it does not change. It does whatever it would do in normal space. So it just goes along normally. This thing could go lower. It could get really close here. It could go down. Doesn't really matter. What matters then is when it gets to a point where there's a hill that needs higher energy to pass than the particle possesses. And because it's quantum, a tiny part of it can sneak through. Now, for big things, right, like if you had a brick wall that's a foot thick and you sent a quantum particle through it, it will not pass through. It's one of those technically not 0, but practically for all intents and purposes until the heat death of the universe 0 kind of problems. It makes sense to think of it as waves. I don't know if you know this about light, but we do optics, we generally think of light as a wave. And you'll know that there's a percent of light that will reflect off of a surface. There will be part of it that refracts into the surface. Some of it will travel through and some of it will be reflected off. If the energy level is lower than the particle, we can think of that as just the light moving through space in a straight line. But when it hits that barrier, that's where we get this splitting into 2 directions. So this here is our probability distribution of where our particle is, which at this point we were just kind of calling it the particle, the wave function, the probability, whatever of the particle. This here is our barrier that is of a higher energy level. That is to say, it is like a hill that is higher than our particle should be able to get to if we're thinking of it as like a ball rolling down a hill. And this one, it's colliding with it, where some of this wave function is going this way and some of it's moving this way, and there is a decay in height inside the barrier, and on the other side, whatever the height of this decay is at the end of the barrier is the height of this waveform going on the other side. And after the whole collision, most of it is behaving as we would expect it to classically, where it didn't have enough, so it bounced off the barrier. But a little bit of it snuck in and out the other side. And that is what quantum tunneling is. Classically, you could not get through this barrier. You could not go over this hill. So we say it tunnels through the hill.
Oh, now is a perfectly fine time to ask why this stuff matters. I think the biggest implication of all this is that if you make transistors, computer parts, too small, there's a non-zero probability that electrons will tunnel through computer parts, and that's no good. It messes up your stuff. But anyways, hopefully this was a bit understandable. Let me know if it wasn't, and I can retry it. I hope you have a good Thursday, and I'll see you on Friday.